All right, so today we'll be talking about angle chasing and similar triangles. It's lecture 3, so this is our third lecture of our 8-lecture series. So we hope that you've taken a look at the handout beforehand, and let's get started. So first, we'll go over some basic definitions. So we won't be defining points, lines, rays, angles, and other basic geometric figures. Because we're assuming that you guys know most of these. And if you guys don't, you guys can ask me because I'm the only instructor here today. And we note that point and lines don't actually have rigorous definitions, so to speak, and they are called primitive concepts. And for the curious reader, so you guys, there are 5 main primitive concepts in plane geometry, and these are called the 5 axioms of Euclidean geometry. So the first one is 1, a straight line may be drawn between any 2 points. 2, any terminated straight line may be extended indefinitely. So that means like a line segment, you can extend like the 2 sides, the 2 ends of the line segment. And then 3, a circle may be drawn with any given point as a center and any given radius. 4, all right angles are equal. So the first 4 might sound pretty intuitive. But then the fifth one says, so the original one says, if 2 straight lines are met by another line, then if the sum of the internal angles on one side is less than 2 right angles, so 2 right angles is 180 degrees, so that's a straight line, right? So if it's less than 180 degrees, then the 2 straight lines will meet if extended sufficiently on the side, which the sum of the angles is less than the 2 right angles. So this is a pretty long axiom, but in the end, it just means that for any given point not on a given line, there is exactly one line through the point that does not meet the given line. So this is axiom 5, and the one that I have in the list here that says for any given point not on a given line, there is exactly one line through the point that doesn't meet the given line. That definition is equivalent to the original axiom. And as a challenge, you guys can try to figure out why these are equivalent, or why are these mathematically equivalent? So in other words, why does one imply the other? All right. Now let's go over some more definitions, right? So parallel lines are just lines in the same plane that never intersect. So if you extend them indefinitely, then they'll never meet, right? A right angle is an angle that can be thought of as a quarter turn for any of the angles in a rectangle. It looks as follows, and a right angle has a measure of 90 degrees. And sometimes you'll see this denoted in a diagram with like the square symbol, like the square angle thing. This looks like a normal angle. It looks more like this, but smaller. All right. And acute angle is any angle that's less than a right angle, so any angle that measures less than 90 degrees. An obtuse angle is an angle that's greater than a right angle, but less than 180 degrees. So it's between 90 and 180 degrees. And an angle of 180 degrees is simply a straight line. So if you have, let's draw using red. So if you have this point here, it's really hard to draw a point. Right, red, so you have a point, right? And then you have this, and this is a straight line. Then the angle that this forms is 180 degrees. Right. And then we say 2 lines are perpendicular if they form right angles, right? So if you have 2 lines that intersect at right angles, then they're perpendicular. And this contrasts with the definition of parallel. And then supplementary angles are angles that add to 180 degrees, and complementary angles are angles that add to 90 degrees. If one way that, sorry, we let someone in. Right, one way that we can remember that supplementary is for 180 degrees and that complementary is for 90 degrees is to use the simple trick. So you can see that S is basically 2 C's, right? There's like 1 C here, and then there's like a backwards C, right? And so that's how you remember that S is equal to 2 times C. That means complementary angles are 9 degrees, and supplementary angles are angles that add up to 2 times 90, so 180 degrees. Right? So that's how I remember it. Or at least how I remembered it. Right. Now I just like you don't have to use that, but if you like ever forget, you can always remember like S is 2 C's. So complementary is 90 and supplementary is 180. Next we have an acute triangle. So that just means a triangle in which all angles are acute. A right angle is a triangle that contains a right angle, right? So the two sides adjacent to the right angle are called legs. So let me draw this. So these are called, this is 1 and 2 are called legs, and then 3 is the hypotenuse, right? The opposite side, and also the hypotenuse is the longest side of this right triangle. An obtuse triangle is a triangle that contains an obtuse angle, so something like this, because this angle is obtuse. So there's many definitions for this lesson because geometry has a lot of them. So this is the last part, right? So an equilateral triangle is a triangle in which all of the sides are equal. And an equilateral is also equiangular. So that means all the angles are 60 degrees. Next, an isosceles triangle is a triangle in which 2 of the sides are equal, and the third is not equal to the other 2. So, well, actually, I'm pretty sure the definition is that at least 2 of the sides are equal. So all equilateral triangles are isosceles, but not all isosceles triangles are equilateral. So an isosceles triangle would look something like this, right? So these 2 sides are equal, but this side doesn't necessarily have to be equal to the other 2. A scalene triangle is a triangle in which all 3 sides are different lengths. And then lastly, when 2 lines intersect, angles that are opposite to each other are called vertical angles. So the angles that are marked out in the diagram below, like here, these are called vertical angles, and 2 angles that are right next to each other are called adjacent angles. So the yellow angle and this blue angle, and this blue angle here would be considered adjacent. Right? So the yellow angle and the blue angle, or this yellow angle, this blue angle would also be adjacent. All right. Lastly, let's review a concept called transversals. So for lines L and M, the line N is called a transversal because it intersects both L and M. And then these red angles are called corresponding angles, and the blue angles, and the lower left angle and the blue angle are called alternate interior angles. So for example, this angle here, the red angle you see between M and N, and this angle to be considered alternate interior angles. And this small blue line that's like right here, and this green angle are called alternate exterior angles. And if L and M are parallel, and if and only if lines, if lines L and M are parallel, then red angles are congruent in measure, and the red and blue angles are supplementary, right? So basically, there's a lot of properties that come across. So I'll mark a few right now, right? So remember that this is in the case that L and M are parallel to each other. So these green angles are equivalent, so any corresponding angles are equivalent. Alternate interior angles are equivalent. Alternate exterior angles are equivalent. And also, a lot of angles are supplementary to one another. So for example, the red one and the green one are supplementary, the blue and the green one are supplementary. Right. But this is if and only if lines L and M are parallel, so make sure to remember that. Now we have angles and triangles. So there are 2 types of angles. One of them is called an interior angle, and one of them is called an exterior angle. It's pretty intuitive. So an interior angle is one that's inside the triangle, right? So this one, this red angle here would be an interior angle, and an exterior angle is outside the triangle. So basically how you make them is you extend one side of the triangle, and then the angle formed between the triangle and that extended line that's not inside the triangle is the exterior angle. And the exterior angle is basically the interior angle, well, 180 minus the interior angle, right? Because they're supplementary. And So basically, yeah, so what it says here, right? So CBD, angle CBD is called an exterior angle because it is supplementary to one of the angles in the triangle, the interior angles. And there are two main theorems for angles and triangles. So they're listed here. So firstly, angle sum. So the sum of the angles inside a triangle is 180 degrees, right? So the interior, sum of the interior angles of the triangle. And then finally, for exterior angles, the measure of the exterior angle in a triangle is the sum of the two opposite interior angles. So that just means that angle CBD is equal to the sum of the two opposite interior angles. So that would be this interior angle and this interior angle. And basically this theorem just says um, the two green angles sum up to the blue angle. Yeah. There are a few minor theorems here. So this is the isosceles triangle theorem. So if two angles in a triangle are equal, then the two sides opposite to them must also be equal. And if two sides in a triangle are equal, the two angles opposite them must also be equal. So what does this mean? Well, if you draw like a typical isosceles triangle, right, and say this side and this side are equal, then you know that these two angles are equal. And similarly, if you have two angles that are equal, then these sides must also be equal to each other. And this can also be derived using the law of sines or something similar. But this is a very important thing to remember because often if you see two equivalent angles in a triangle, then you know, then it must be isosceles. And that can be very helpful, especially like in proof problems. I feel like it's very important to establish relationships between the sides and the angles. And lastly, but not least, last but not least, we have the famous Pythagorean theorem, right? So if you have a right triangle with a right angle at B, then it's right if and only if AB squared plus BC squared is AC squared, right? Right. And now let's finally talk about some similar triangles. So we call two triangles similar if they are the same after a stretch or a shrink, also known as a dilation. So more precisely, a similar triangle can be identified in the following three ways. So you often hear them refer to it as like AA similarity, which means angle-angle similarity, or they'll call like SSS similarity, right? So let's go over each of them. So AA, two triangles are similar if and only if two angles in the first triangle are equal to the two angles in the second triangle. And SSS says two triangles are similar if and only if corresponding sides are in equal proportion, right? So each side length is some constant multiplied by each side length in the other triangle, right? And SAS just says if two triangles are similar if and only if two pairs of corresponding sides are in equal proportion and the angle between them is the congruent for both triangles. So for example, you can use this side, and this angle, but you can't use like this side, and like this angle because it has to be the angle in between the two sides, right? So side angle or SSA does not work except for special cases, and it can be an exercise to figure out in which special cases does SSA work and why does it not work for other cases, right? So these are the three major concepts for similar triangles and how to prove that they're similar. So AA, angle, SSS, so side, then side, angle, side, SAS. So, and remember that because A is between the two S's, it means that there's an angle between those two. All right, so now let's do some examples using the theorems that we mentioned before. So first, let's find the missing interior angle in the triangle with the two other interior angles being 30 and 60. Well, we know that the sum of the angles in a triangle is 180, right? So that means the last angle has to be 180 minus 30 degrees minus 60 degrees is equal to 90 degrees. All right, that was pretty easy. All right, now the next one says find the missing interior angle in a triangle with the other two exterior angles being 100 and 110. So remember that exterior angles are supplementary to interior angles. So that means that the interior angles in this case would be so the interior angles would be 180 minus 100 equals 80 degrees. The other the other interior angle would be 180 minus 110 equals 70 degrees. Okay, my handwriting is horrible. Let me fix this. Equals. All right. And then lastly, I want to find the missing interior angle, right? So 180 minus 80 minus 70 equals 30. So that's the missing interior angle. All right, now we'll move on to some harder ones. So this is a problem taken from an AMC 8. So the degree measure of this angle A is, so we want to find the degree measure of angle A, right? So first, let's just figure out some angles, right? So first, we can figure out this red angle here because they're supplementary to an angle of degree 110. So this red angle here is 70 degrees. Now, we know that the sum of the angles in a triangle sum to 180. So that means this triangle here, this angle here is also 70 degrees, right? Because 180 minus 40 minus 70 is equal to 7. Yeah. And unrelated to this note, remember that we can use the isosceles triangle theorem to note that these two sides are equal, but that's not relevant to finding the answer to this problem, right? Next, we know that vertical angles are equal to each other, right? So that means this red angle here is also equal to this red angle here. So this is also 70 degrees. That looks like 80. So this is also 70 degrees, right? And then we also have this blue angle here that's supplementary to the 100-degree angle, so that would be 80 degrees. All right. And finally, the angle for A, the angle measure of A would be 180 minus 70 minus 80 because the sum of the angles in a triangle is 180 degrees. So 180 minus 80 minus 70 would be 30 degrees. So our final answer is A is 30 degrees. Right. Okay. So next, we have in triangle ABC, D lies on side BC such that AC equals CD and the angle CAB minus the angle ABC is equal to 30 degrees. What is the measure of angle BAB? So the first thing I should do in every geometry problem is draw a diagram and make sure the diagram is large so that you can add stuff to it and make sure that it's accurate. It doesn't have to be like very, very, very specific and accurate, but like if you have a decently accurate diagram, you can often deduce things just by looking at the diagram alone. So for example, you might guess that these two angles are equal, but you would go through the process of finding them first. Right, so let's draw a diagram first. So we have a triangle ABC, right? The A, B, C. And we have D on the side BC here, and AC equals CD. So AC is equal to CD. Here. And then we have that angle CAB minus angle ABC is equal to 30 degrees. What is the measure of angle BAD? Right, so let's use some variables to represent some angles. So if we call angle CAD alpha, we can use the isosceles triangle theorem to deduce that angle CDA must also be alpha. Yeah. And then we can use the fact that the sum of the angles in a triangle is 180 degrees to deduce that angle C is 180 minus 2 alpha, right? And then next we can find that angle ADB. So angle ADB would be 180 minus alpha because it's supplementary to angle CDA. And then lastly, let's call this angle DAB equals beta, right? And then once again, using the fact that the sum of the angles in a triangle is 180, we can find that angle DBA is equal to alpha minus beta. Now we'll notice that we haven't used one fact yet, which is that angle CAB minus angle ADC equals 30 degrees. And this is a key concept when you're solving geometry problems. You want to make sure that you're using everything that the problem is telling you. Sometimes, for example, in like school tests, they'll give you extra information to confuse you, but usually in competition, they'll give you the bare minimum that you need, which means that you need to use every single piece of information that they give you. All right, so they ask you to find the degree measure of BAD, right? So, and they also give you that CAB minus ABC is 30 degrees, right? So angle CAB is a plus beta, alpha plus beta, sorry. And then angle ABC is alpha minus beta, right? Because I marked out these two angles, right? So alpha, this is angle CAB, and then the blue angle is CAB, and this red, screen, this green angle is angle ABC, right? So we have that alpha plus beta minus the quantity alpha minus beta is equal to 30 degrees. That just means that 2 beta, right? If we solve this equation, we have 2 beta is equal to 30 degrees, which means beta is equal to 15 degrees. And now if we go back to the original problem, we want the angle measure of BAD, which is beta. So we've solved the problem. All right. Yeah, so sometimes if they don't give you initial angles, just set variables to be equal to those angles and then angle chase for a while. Sometimes you'll end up in a loop where everything just satisfies another thing. So you might want to introduce more than one variable. Sometimes it can just be solved with one variable. So it's up to the problem. Right. Let's tackle some similarity problems. Drink of water. All right. So example 3.1. Triangle ABC has side lengths of 3, 4, and 5. Sorry. And then triangle DEF has side lengths of 6, 8, and 10. Determine whether triangle ABC is similar to triangle DF. So yeah, the notation for similarity is like one of these squiggly symbols. You'll often see them in like approximations, but it's just instead of two of them, sorry, you just have one of them to denote similarity. Right, so that's just the similarity symbol here. All right. So determine whether they're similar triangles. Because we have 3 side lengths from ABC and 3 side lengths from DEF, we can use SSS to verify that they're similar. So 6 is equal to 2 times 3, 8 is equal to 2 times 4, and 10 is equal to 2 times 5. Right, so you can see that it's just ABC scaled up a factor. Something else to note is when you write that triangle ABC is similar to some other triangle DEF, what you're also saying is that AB corresponds to DE. You're also saying that BC corresponds to EF, and you're also saying that AC corresponds to DF. Furthermore, you're saying A corresponds to D, B corresponds to E, and C corresponds to F. So when you write these statements, the order that you put the letters in, the letters that correspond to the points, that is, the order that you write the statement does matter, right? That doesn't, the commutative property still applies, right? So if ABC is similar to DF, then DF is still similar to ABC. But what I'm saying is, so for example, ABC is similar to DEF, but ACB would not be similar to DEF. It would be similar to DFE, right? Because you have to make sure that the letters correspond to one another when discussing similarity. Okay, so let's do another example. This one uses similar triangles as a hint, right? So we have a figure, right? And in the above diagram, we have that AB equals BC, right? So AB equals BC. Nice. And then we also have that BF is equal to FE. So BF is equal to FE. And then we want to see if CD is equal to 38, we want to find DE. Now this configuration here, just as an added note, this is not like relevant until you get into more advanced mathematics or advanced Olympiad geometry. But this configuration is called a complete quadrilateral, and you'll have a lot. This situation is full of similar triangles, and in this case, what we want to do here is we want to draw an what we call an auxiliary, right? So auxiliary, which just means like something that doesn't exist in the given diagram, but something that we can construct, and that will help us solve the problem, right? So in this case, what we want to do is we want to draw a line parallel to CE through B. So if we draw this line here, this is our auxiliary element. Let's call this L, right? So what we'll notice is first we see that EF is equal to FE, right? And then we can use the properties of transversals that we discussed in 1.1, right? This configuration here, because we know that the two lines are parallel to one another. So if we go back down to the example, we have that this line L is parallel to CE, which means that if we zoom in a bit, right, we notice that this angle, this green angle, that is formed by the line and BE, as well as this angle, is equivalent to one another because they're alternate interior angles, right? And we also know that this angle here is equivalent to this angle because they're vertical angles, right? And now what we can deduce is that these angles are not only similar, but they're also congruent. And this is called ASA congruency, right? So there are various, similar to similarity, there are also various types of congruence, right? They all mean congruence, but there's a few ways to deduce congruence. And I'll write them here on the side. They are side, 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 angles, side, angle, side, and angle, side, angle, side, angle. And basically what this means is SSS means all three sides are congruent to one another, so they're the same one. SAS means two sides are congruent to one another, and the angle in between them is also congruent to the angle in between in the other triangle. And then lastly, ASA means two angles are congruent, and the side in between those two angles is congruent as well, right? And you'll notice that ASA and AAS, or sorry, SSA and AAS do not apply in this situation either. It's only SSS, SAS, and ASA. And notice that AAA is not in there either because AAA only means similarity and not congruency. Because when you enlarge a triangle, when you enlarge this triangle here, right? Assume that the triangle doesn't look similar, but assume that it is similar. You'll see that the angles are still the same. So that means AAA does not apply, right? So the only ways to prove congruence are SSS, SAS, and ASA for triangles. And there are special cases for right triangles, but for now we just know SSS, SAS, and ASA. All right. Now proceeding on, we have that this triangle here, this yellow triangle, is congruent to this blue triangle. So what this also means is that DE is equal, so these two segments are equal. Let me use green, I guess. If we call the intersection between the line and AD is, let's call it P, right? Then we know that this side here, BP, is equal to DE, right? Because of the principles of similarity. Sorry, the principles of congruence, not similarity. And then also we have that a triangle ABP is similar to triangle ACD, right? Because ABP, in ABP, this angle, this red angle here, is congruent to this red angle down here by corresponding angles in a parallel line, right? For a transversal through parallel lines. And then we also know that this angle is this red angle APB is equal to the angle ADC, also by the properties of parallel lines and the transversal through them, right? Because they're corresponding angles. And then so we know that ABP is similar to triangle ACD. Alternatively, you could have just looked at one of them and realized that angle BAP is equal to angle CAD. But that's besides the point. We can use these two to further reinforce our understanding of transversals and corresponding angles, right? We also then lastly we know that DE is equal to PB, but we also know that PB is the ratio between triangle ABP and triangle ACD is 1 to 2, right? Because AB is equal to 1/2 of AC. And we know this because in the problem statement, they gave us that AB equals BC, right? So you notice that we used both AB and B equals BC and BF equals FE, and we'll later use C equals 38, right? So these are, you'll see that every piece of information is used. And lastly, we have that we just need to use the properties of similar triangles, right? So BPF is congruent to FDE, right? So sorry, BPF is congruent to EDF, right? So we have that that's from, we also know that DE equals BP. So we're finding DE, we have to find DE, but this is also equal to BP. Okay, so let's find BP instead. So BP is equal to 1/2 of CD because ABP and ACD are similar, right? We have ABP similar to triangle ACD by AA. All right. And then finally we have that the ratio is 1/2, right? So that means BP is equal to 1/2 times CD, which is equal to 38 over 2, which is equal to 19, right? Let me erase this. 1, 9, all right, 19, right? So walking back through this problem, we first constructed this auxiliary line here, this line L that's through B and parallel through CE. We noticed by axiom 5, now you don't have to cite this now, like if you're like showing your work, but by axiom 5, you know that this is also the only line that exists, right? Then we used ASA to show that BPF is congruent to EDF. And then we used similar triangles to find DE, which is equal to BP, right? So, and then we deduced the ratio is 1 to 2 because they gave us that AB equals BC. And so the BP was 1/2 of CD, which is 38. So BP is 19. So our final answer is 19. Here. And the ASA congruence, if you guys want to come back to this lecture for future reference, the congruence is triangle EDF is congruent to triangle BPF, right? Now let's do, all right, before we move on to the next few examples, let's go over some special right triangles. So these come up very often. They're called the 30, 60, 90 triangle and the 45, 45, 90 triangle, which is not yet drawn, but I'll draw it very soon. Right, so basically you just have to know that this is a special right triangle and the sides are in a proportion of 1 to √3 to 2, right? And this is the side opposite. Remember, this is the side opposite, not the side adjacent, the side opposite, right? The side opposite the 30-degree angle, the side opposite the 60-degree angle, and the side opposite the 90-degree angle, right? So the side opposite the 30-degree angle to the side opposite the 60-degree angle to the side opposite the 90-degree angle is always going to be 1 to √3 to 2. And let's go over the 45, 45, 90 triangle because that's also one of the most common right triangles, right? The two most common right triangles are 30, 60, 90 and 45, 45, 90. So 45, 45, 90 looks like this. Uh, you have uh, you have two legs that are the same length. That looks really bad. Here, so bad. Okay, so this is 1, and this is root 2. This is 90, this is 45. This is 45, and this is 45. Okay. So it's basically the same thing. It just means that these side lengths will be in a ratio of 1 to 1 to root 2. And this is the side opposite the 45-degree angle, the side opposite the 45-degree angle, and the side opposite the 90-degree angle. Okay. Okay. And these are just the two common right triangles that generally, if you want to do like a quick computation, whenever you see these types of triangles, you have to know this by heart, right? So these are the two most common special right triangles that you'll see, besides like the equilateral triangle, I guess. All right, let's do one more problem. We have, let's see how many more examples. We have three more examples, including this one. And if we have more time, we can go over more. All right. So now we have this problem here, 3.3. Suppose ABCD is a convex quadrilateral with angle ABC equals 144 degrees, angle ADC equals 105 degrees, and AB equals BD equals DC. And we want to find the difference between angle BCD and angle BAD. So let's draw a diagram first. So we have a convex quadrilateral with ABC is 144 degrees. And then the side opposite that has an angle measure of 105 degrees. So that's right. A, B, C, D. 144. This is 105. Right. We also have that AB is equal to BD is equal to DC, right? By the way, these hash marks that I've been using, these just mean like the sides are congruent to one another. And I know I said that it's important to have a really good diagram for doing geo problems. But I'm drawing with my finger on a screen, so it's not very clean. But when you draw at home, when you're on pencil and paper, when you have like a ruler or a compass, if the contest allows, then please use a ruler or a compass. Especially for harder problems. For easy problems, you can like do like a rough sketch, just using a pencil and keeping it as straight as possible. But for example, for harder competitions, like maybe like the Amy or like I don't know, the JMO or AMO, when you get to that level, then you definitely need like a ruler or a compass or some sort of good geometry drawing skills. Right. All right, and then we have that they want angle BCD, which is this angle minus angle BAD. So these are the two angles that we want. I'll make them different colors to show that they're not the same. All right. Okay. Let's see how I want to do this. So first we can call the angle DCB. So this angle here, we can call this alpha, right? We'll go with the same as before. We can assign some variables. So let me erase the 100 and the 144 very quickly. Right. Because that's cluttering up our diagram, and we just have to remember that those conditions exist, right? So if we call this angle alpha here, and let's call the other angle that we want beta, right? Well, first, we have that BD equals DC, and that just means BDC is isosceles, right? So using the isosceles triangle theorem, we also know that angle DBC is alpha. And that means that angle BDC is 180 minus 2 alpha. 180 minus 2 alpha, right? And then we also have that angle ABC is equal to 144 degrees, right? So that means that this angle here is 144 minus alpha degrees. And then lastly, you also notice that oh wait, sorry, I messed up for a second. Hold up. All right. So you also notice that AB triangle ABD has AB equals BD. So using the isosceles triangle theorem again, we can realize that this is also beta, right? And then we can use the properties. We can use the fact, sorry, that angle ADC is equal to 100 degrees as said in the problem, right? It says that in the problem, angle ADC is 105 degrees. So we can use that as well. So that means that angle ADC is 105 minus beta. And now we just see we have a system of, two equations, right? So, right, yep, that's fine. If you need to go, you will be uploading our recording, but stay for now. If you don't have anything, if you don't have extenuating circumstances. All right, so now we have our diagram, right? So now let's set up our system of equations. So we have 180 minus 2 alpha is equal to 105 minus beta. We have 180 minus 2 beta is equal to 144 minus alpha. Right? What we have from here next is we have 2 alpha minus beta is equal to 75. And then we have that 2 beta minus alpha is equal to 36. And then we can just multiply this by 2, add these two equations together. Right, we have 3 beta is equal to 175 plus 72, which is 147. So what we get is that beta is equal to 49 degrees. Right. We have beta equals 49 degrees. And we have alpha is equal to, well, we can just plug beta back into like this first equation here. So let's call this one. If we plug beta back into this equation here, we'll have that alpha is equal to, let's see, 62 degrees. Right, let me check to make sure that's right. 62 times 2 is 124 minus 49 is 75, right? So we have alpha and beta. And now let's look to see what the problem was originally asking. The problem originally asked for BCD minus angle BAD, right? So BCD we see is alpha, right? And then BAD is beta. So what we want is alpha minus beta. That was 62 minus 49, which is 13. Right. So our final answer is 13 degrees. Right. 2 more examples. We have in this diagram here, we have that AB and AC are equal sides of an isosceles triangle ABC, in which is inscribed equilateral triangle DEF. Designate BFD by A, ADE by B, and FEC by C. Then find A in terms of B and C. All right, so this problem is rather nice. They gave us a diagram already. So that's nice. Now, what we want to do is we can set up some equations, right? So in an equilateral triangle, all of the angles are also equal to one another. So an equilateral triangle is also equiangular. So that means that each of the angles is equal to 60 degrees. Now, what we'll notice is that means that because the sides, so for example, all of these angles will add up to 180 degrees, right? Because they form a straight line. So we can set up a system of equations based on that, right? So we can write that, right, I'll keep the diagram up here for you guys to look at. We'll have that angle FDB. So if you take a look at that angle on the diagram, that is equal to 180 minus 60, so that's 120. 120 minus B. Similarly, we also have that angle EFC is equal to 120 minus A minus A. Okay, cool. And then we also have that the angles in a triangle add up to 180 degrees. So we have that angle ABC is equal to 180 minus sorry, angle ABC is equal to 180 minus A minus 120 minus B, which is equal to 60 plus B minus A. And similarly, we have that, right, so similarly, we have that angle ACB is equal to 60 minus C plus A, right? But then we look back at the original problem, right? So in the original problem, we have that here, right? AB and AC are the equal sides of an isosceles triangle ABC. So once again, we're saying that we're using every single piece of information to solve the problem. Sorry. Right. So if we equate these angles to be equal to one another, we have using the isosceles triangle theorem, right? AB equals BC, so angle ABC equals angle ACB. We can equate these angles to be equal. So we have 60 plus B minus A is minus A is equal to 60 minus C plus A. All right, and that just means, well, the 60s cancel, and we're left with B plus C equals 2A. And we noticed that what we wanted was to have, sorry, I think something crashed. Let me pre-share my screen. Sorry about that. Here, we're back. So we have that B plus C equals 2A, and lastly, what we wanted was to find A in terms of B and C, right? So that means we want A on one side alone. So A is equal to B plus C over 2. And that is our final answer. So you see that we just use the fact that DEF is equilateral in some way, and then we just angle chased using pretty simple properties, right? We just use the fact that the sum of two angles is, the sum of the angles on a triangle is 180 degrees. And then we also use the fact that that each angle in an equilateral triangle is equal to 60 degrees. And that's all we needed to get our answer. All right, one last example. So here we have triangle ABC has AB is equal to 2 times AC. Then we also have that let D and E be on AB and BC, respectively, such that angle BAE is equal to angle ACD. And then we want let F to be the intersection of segments AE and CD, and suppose that triangle CFE is equilateral. What is the measure of angle ACB? Well, first let's draw this diagram, right? All right, so we have angle AB, triangle ABC has AB equals 2 times AC. Oh, that's too low. And so let's draw the diagram. That's a little bit too long, but it's okay. We have that AB is 2 times AC. So this is AB, this is C. Right. And then we have D and F, D and E on AB and BC respectively. So that angle BAE, so angle BAE here is equal to angle ACD. So ACD, something like this. Cool. So these angles are equal to one another. Let's shade that with the color. All right. And then we have that F is the intersection of A, E, and C. So let's label E and C and D first. So D is on AB, E is on BC, right? And then we have this is point F. Right. And then we also suppose that CFE is equilateral, and we want to find ACB. All right, so the first thing we'll notice is once again, we can use the fact that each angle in an equilateral triangle is 60 degrees. Right, so let's zoom in on our diagram and let's label those. Right, so let me actually make these labels smaller too. Oops. Right. So we have that this angle is 60 degrees, this angle is 60 degrees, and this angle is 60 degrees. Now what we also know is that this angle is 60 degrees because vertical angles are equal to one another. And then we also know that this angle here is 120 degrees, and this angle here is 120 degrees. Right? So if we let this angle equal x, right, we know that angle BCD is equal to angle AEC, which is equal to 60 degrees. So that's just using the fact of the equilateral, right? And then we also know that angle EAC, this angle here, this green angle here, is equal to, let's see, so 120 minus 60 plus x is equal to 60 minus x, right? So that means that angle CA, so if we zoom out, we see that angle CAB is equal to 60 degrees, right? And then we also see that because AC over AB is 1/2, then we know that triangle ABC is a 30, 60, 90 triangle, right? Because if we draw a simple 30, 60, 90 triangle, we see that the sides are a ratio of 1:3:2, right? With this angle being 60 degrees. And now we see that we're using SAS similarity, right? Angle A, so if we call this DEF, for instance, angle A is similar, angle A is equal to angle D, right? They're both 60 degrees. We also know that DE to DF is 1 to 2, and AC to AB is 1 to 2. So now we know that triangle ABC is indeed a 30, 60, 90 triangle. And that is really crucial to helping us solve the rest of the problem, right? Because what do we want? We wanted angle ACB. And C corresponded to E in a typical 1√3, 30, 60, 90 triangle, right? So that means that C is the right angle here. So that means angle ACB is equal to 90 degrees. Right. So we see that this problem basically just boiled down to recognizing that the triangle is a 30, 60, 90 triangle. Now you notice that in my diagram, I purposely drew it so that it did look like a right triangle. And you'll see like that would be really important. If you drew a triangle that didn't look like the right triangle in the beginning, and then you tried to figure out like using SAS similarity that it was a right triangle, that would be much harder than say drawing a very good diagram in the beginning and then realizing, wow, angle ACB looks like a right triangle. Is there any way that I can prove that it's a right triangle? And then you'll see, wow, after doing some angle chasing, we found that the angle in between AC and AB, so angle CAB is 60 degrees, and AC to AB is 1 to 2, given in the original statement. then we'll see. Okay, so now we know that angle ACB is 90 degrees because of the 30, 60, 90 triangle. So once again, to reiterate, it is very important to look at every single aspect of this problem, right? We used literally everything in this problem. We used the fact that AB equals 2 times AC. We utilized the fact that BAE is equal to ACD, right? And then we also use the fact that CFE is equilateral, right? So in competition problems, you'll see that every single part of the problem is utilized typically. Right, it's almost 7:15, so we don't have any time for any additional examples, but I got through everything that I wanted to today. So a few closing remarks before you guys can go. The first thing is we have handout 3 is posted on our website with problems that you can try yourself, and we'll be posting solutions to that I'd say before our next lecture. And our next lecture is on introductory counting techniques. And our next lecture will be this Saturday, July 17th, I think. Yeah, July 17th from 10 to 11. This is the next lecture is the first lecture that Threya will be back. He had an emergency, which is why he could not be here for the first 3 lectures, but he'll be back for next lecture, and I actually won't be there for the next lecture. And lastly, we also have the solutions to the second problem set. So the solutions to the problems on handout 2, those are posted as well. So you can take a look at those if you did the problems. And that's basically it for today. Thank you everyone for coming, and we'll see you at our next lecture Saturday, 10 to 11 a.m. The 17th.